Okay, so this is section 16.3, video number 2. In video number 1, we kind of learned how to we learned how to deal with the fundamental theorem for line integrals by just kind of finding the original function, and then we kind of defined what the fundamental theorem for line integrals is, assuming that we have bounds, which we hadn't dealt with yet. So in problem number 3 here, it says find a function f such that capital F is the gradient of lowercase f. That's what we did in the last video. And then use part A to evaluate the line integral of f dot dr along the given curve C. So we're actually going to do this one in 2 different ways, or at least we're going to start one of them 2 different ways. So the first thing it says, well, it's actually not the first thing, but it wants us to find the line integral of f dot dr. That's the ultimate goal here. So we already know ways to do this. So if we do this like from, we'll say from section 16.2. So from section 16.2, we know that we can do the line integral of f dot dr, which is the same thing as the integral of f of r of t dotted with r prime of t dt. And then that would go from t1 to t2. So let's go ahead and at least try to do this one. So first thing is we're going to need f of r of t. So we need to kind of define r of t. So r of t, well, let's see. The x is going to be, what is x here? X is going to be the square root of t. That comes from here. Y is going to be 1 plus t cubed. Yeah. So I'm not going to write the r of t part down there. So we need to do f of r of t. So that means we have to evaluate our function at r of t. So let's see. F of r of t. Oops, capital F. This is where it's going to get confusing. I got to keep the capital and lowercase f's straight here. So if I plug in x, which is square root of t, into here, we're going to get t to the 3/2 power, t to the 3/2, and then y is going to be 1 plus t cubed to the 4th, 1 plus t cubed to the 4th. And then we got to do the same thing over here. So this one will be a little bit nicer because that's going to give me t squared. And then 1 plus t cubed cubed. So there's f of r of t. I'm also going to need r prime of t, which is the derivative of each one of the x and y pieces. So the derivative of square root of t is 1/2 t to the negative 1/2, or 1 over 2 root t. And then the derivative of 1 plus t cubed is just 3t squared. And then when we do this, we're going to have to dot those 2 things and take the integral. Fortunately, it tells us the integral goes from 0 to 1. So we're going to take this integral from 0 to 1. Let's see, the dot product now is going to be t to the 3/2 times 1 over t to the 1 over 2 square root of t is going to give us, let's see, that's just going to give us a t, so it'll be 1/2 of t. 1/2 t. Still got to bring in that 1 plus t cubed to the 4th. That's the dot product, excuse me, that's the multiplication of the x components. The y components will be a little bit easier. That's just going to be 3t to the 4th times 1 plus t cubed dt. And this is probably about as far as I want to go on this one. This could be integrated. There's really 2 ways you could go about doing this. U substitution is not going to work here for either one of these things. I'm not going to be able to do U substitution and solve this easily. This was a pain pain to integrate. You could do this in one of two ways. You could use a calculator. Or the other way to do it, and this would take a while, you could expand 1 plus t cubed to the fourth and 1 plus t cubed cubed, then distribute all the pieces, then take antiderivatives, and that's going to take a long time. So I would definitely suggest, if you're going to do this one, to do it in your calculator. Ultimately, what I can tell you is that the answer to this is 4. No, I did not actually do this one in my calculator or actually do this one longhand. I just know that the answer is 4 because I'm going to show you the other way that we just learned today. So from our new section, 16.3, because of the fact that it says f equals the gradient of f. Okay, it's telling us that up in part A there. It says, find a function lowercase f such that capital F is the gradient of lowercase f. So it's telling us that this has to exist. Well, if that's the case, then let's define the gradient. The gradient of f is going to have to be x cubed y to the fourth, x to the fourth, y cubed. Okay, that's given to us. It's telling us that. So then now we can go to the process that we just learned how to do, which is letting f sub x, or the partial with respect to x, equal the first component, x cubed y to the fourth. Take the antiderivative with respect to x. So f here is going to equal, that is an x cubed there, so it's going to equal 1/4 x to the fourth y to the fourth plus some function of y. That's our constant in this case. We also know that f sub y is defined to be x to the fourth y cubed. Taking the derivative of our f function with respect to y to get a matching, let's see, with respect to y, we bring the 4 out to the front, multiply it by the 1/4, then we reduce the power of the y by 1. So x to the fourth y cubed plus the derivative of g of y is g prime of y. Once again, you should see that these two things are equivalent, and the x to the fourth y cubes match up, so that means that g prime of y is 0, because there's nothing left over for me to match it up with, which means the antiderivative, so g of y, is going to be some constant k. So my original function, f, is going to equal 1/4 x to the fourth y to the fourth plus k. So that's actually part A. Now part B says to use what we found in part A to find the line integral. Well, because we know that capital F is the gradient of f, the fundamental theorem for line integrals says that the line integral of f dot dr, which is what we are trying to find on the left-hand side there, is lowercase f of xy evaluated from a to b. But remember that a and b are t values. Oops, this one is associated basically as t1, this one is associated as t2. But we can't use t values because our function here is a function of x's and y's. So what we need to do is we actually need to find a and b, but a and b in this case are, because this is now two-dimensional, a and b are points. They're actual coordinate points. So a and b are points. Well, how do we find a and b? Well, if we take, in this case, this went from 0 to 1. So T1 was 0, T2 was 1. If we take 0 and we plug it back into our curve right there, let's see, if you plug in 0 for t, you're going to get 0, comma 1. So A is the point 0, 1. B is plugging in 1, so we're going to get the square root of 1, which is 1. And then 1 plus 1 cubed is 2. So B is the point 1, 2. So now we can utilize the fundamental theorem for line integrals, which says that line integral f dot dr is going to equal our original function, which is 1/4 x to the 4th y to the 4th. Now we really don't need the k here because the constant's going to go away. Evaluated from the point 0, 1 to the point 1, 2. So if I plug the point 1, 2 in first, let's see, we're going to get 1/4 times 1 to the 4th times 2 to the 4th minus, now if I plug in 0, 1, I'm going to get 1/4 0 to the 4th, that's nice, 1 to the 4th. So that whole last part's going to be 0. So really all I'm going to get is 1/4 times 1 times 2 to the 4th, which is 16. 16 over 4 is 4. And that actually matches exactly what we got, or what I told you that we were supposed to get from the first one. So you could definitely plug the first one into your calculator just to make sure that it matches, just to make sure you get the same thing, but it will. So, again, what does that mean? It means that your line integral over C of f dot dr is the antiderivative, or the original function f, evaluated from a to b, which is exactly the same thing as f of, I'm going to write this a little weird, r of b minus f of r of a, where r was your original, where r was your original curve right there. So you have to plug in the t values back into that to get your points A and B. And now here's the really interesting part about this. What you should hopefully notice, and if you didn't, I'm going to spell it out here for you. Look at the way we did this in 16.3. I'm going to put kind of a dotted line down here just to separate this. What you should notice is the way we did this in 16.3 didn't utilize the force vector at all. Other than the fact that they told us that the force vector is defined as the gradient, we didn't utilize that within our integration or any of our antiderivative stuff at all. So the line integral here doesn't actually matter what's happening with the force vector. So let me just kind of like sketch, here's some kind of a vector field. You know, it's got vectors doing all kinds of crazy stuff. Whatever these vectors are doing, I don't know. Something like that, who knows exactly what the vector field is. What this said was that we started off at, what point did we start off? The point 0, 1, which is about right here. And we finished off at the point 1, 2, which, you know, maybe is right about here or so. So what this says is that it only matters where those points are. And it doesn't really matter what's happening in between. So I could take a path which does this. Goes here, comes up here, back around here, and then finishes right there. Okay, I could take that path. I could also take this path. This direction, curling over here, and then finishes up there. Or I could take, I'm going to run out of colors here. I could take this path. Might do this and curl a bunch of times and come around this. It doesn't make any difference which direction I go over this force field, over this force vector field. All that matters are the endpoints. Now, again, this is assuming this. It's assuming that the vector field can be defined as the gradient of f. If that is the case, it doesn't make any difference what happens in between. It only matters about the endpoints. Okay, that's a really actually important concept. So I'm going to kind of put that into actual like terminology on the next page here. So we're going to write a sentence about this one. So it's going to say if capital F can be defined as the gradient of lowercase f, then the line integral over C of f dot dr is just going to equal the antiderivative evaluated at r of b minus the antiderivative evaluated at r of a, which again are just points, and the line integral is, and this is the important part here, independent. Try and actually write that nicely. Independent of path. Meaning it does not make any difference which way we went. Or all that matters about C are the endpoints. Okay, kind of a cool concept. Doesn't really matter which path we take to get there. It's going to be the same result no matter what. Again, this is only if the capital F, if your vector field can be defined as the gradient of lowercase f. So there's a corollary to this, kind of a really cool corollary to this, and hopefully this will make some sense. If I start here and I go, I don't know, the path might go this way and then around here, and then all of a sudden I end up right where I started from. The corollary, I think it's two R's, one R, I can't remember, I think it's one R. Corollary, I think that looks right. Corollary, if C is a closed curve, then the line integral of f dot dr equals 0. And again, this is still all assuming that capital F is defined as the gradient of lowercase f. And that should make sense, because if you start and you end at the same place, if you plug the same exact point into f of r of b and f of r of a and subtract them, you're going to get 0. So it's got to be a closed curve. Okay, starting and ending at exactly the same place. All right, pretty cool stuff. All right, so now let's take a look at when can this happen? Because that should be a question as well. How do I know? Unless they specifically tell me, how am I going to know this? When can this be the case? So let's look at a vector field maybe where capital F is defined to be something like xy and then xy plus x. Okay, this is going to be one where this doesn't work out. And the reason for that is, I mean, that is a vector field for sure, because this will not happen over every vector field. But we can't actually write this one as the gradient of f. Because if you were to do it, if you were to actually work this out, that means that f sub x would be xy the antiderivative with respect to x would be 1/2 x squared y plus some g of y. But then we'd also know that f sub y would have to be xy plus x. And if we take the partial with respect to y from the f part, you're going to get that fy equals 1/2 x plus g prime of y. Those two things don't match at all. There's no way to match any of the pieces because that 1/2 x doesn't match anything from the top one. So in this case, this cannot be written whoa, that was weird. I don't know what just happened there. Anyway, this cannot be written as the gradient of f. Okay, there's just no way to do it. So, if something can be written as the gradient of f, here we'll put this in purple. So, part A to this, I guess we'll say, if capital F can be written as the gradient of lowercase f, then capital F, or the vector field, is called a conservative vector field. So this kind of goes to that question that we had up in the top. If capital F can be written as the gradient of lowercase f, then capital F is what is known as a conservative vector field. Okay, that's the first part. The second part to that is that all conservative vector fields are independent of path. So if we know that the vector field is conservative, it is independent of path. Okay, and in part C, which is probably the most important part of this whole thing, is kind of how we're going to determine. So let F be conservative. So we are stating now that it is one of these things above. If that is the case, we can define capital F as some kind of a function of xy I plus some other function of xy j. And we typically use capital P and K for this in 2 dimensions. Well, if that is the case and f is conservative, then that can be defined as the gradient. So we can write that as P of xy q of xy. So if this is the gradient, if this thing right here represents the gradient of lowercase f, because we're defining it to be conservative, we know this is the case. Then that means that f sub x is P of xy, and f sub y is Q of xy. Okay, and here comes the important part. Here comes the end-all be-all to this. One thing that we should hopefully remember, and this is going back a ways, but this is what we should remember, is by Clairaut's theorem, the second partial derivatives are equal to each other. So if I were to take f sub xy, that should equal f sub yx. And that's what Clairaut's theorem states. Well, I know what f sub x is. That's P of xy. So then if I want to find f sub x, y, that's going to be the partial of this with respect to y. So what that's going to be is dp dy, the partial of p with respect to y. Likewise, if I want to find f sub yx, that means I have to take the derivative of this one with respect to x. So that means that fyx is going to equal dq dx. Those are the second partials. And by Clairaut's theorem, dp dy has to equal dq dx. This right here, we'll say then, this right here is going to be how we're going to determine whether something is actually conservative and whether we can write the force function. Excuse me. I knew I was going to sneeze. That's why I messed up my word. The force vector field as the gradient of f. All right, and again, this video is running way too long, so I will come back with a third video, and we should be able to finish off these examples there.